have defined the capacitance as the ratio of the charge to potential value. So whenever you have a given conductor with the proper material and geometry, then you have one unique capacitance value. Right? And we also talked about how to solve for capacitance. Now, we can assume voltage difference, or we can assume how many charges are being deposited over the conductor. So we already talked about two strategies to solve for capacitance. And today I really want to describe a new third way. And this is quite essential because to our understanding, a capacitor is a device that can store electric energy. Right? So somehow we have to associate the capacitance to the energy being stored in a given capacitor. All right? So today, let's try to find out the stored electric energy over a capacitor, and then somehow we can deduce the resulting capacitance. Right? So we are going to look into two different cases. This is another way we're trying to introduce electrostatic energy. So electrostatic energy can be stored in charges, right? If we have a charged particle, it can set up some kind of field distribution, and therefore energy is being stored. Right? On the other hand, if in space we don't really have charges, we don't have the real particle that contains charges, but we do have fields, that space can also be said a field with energy. Okay? So charges can give rise to energy, and also fields, where you don't really have the charged particle, but you only have field lines, but that is also containing energy as well. Alright, so we're going to talk about two different cases. So the first thing, we're going to look into the energy stored for charges. So here, I have two charged particles, right? I have charged particle 1 and charged particle 2. So I want to look into the energy being stored in this simple system. The first viewpoint is, well, I can think of initially I have charged particle 1 sitting here. And then I can bring the charged particle 2 from infinity to here. With the presence of charged particle 1, it generates its field pattern, a radiant field pattern. And somehow, when I'm bringing the second particle to this location, I have to do work. I need to counteract the field being generated by the first particle. Right? So I have to do work, and therefore, if I bring the charged particle 2 to here and let it go, the system is already filled with energy, and that energy amount is equal to the work I have done. Okay? So the energy is Q2V2. The charged amount of particle 2 multiplied by V2, but you have to understand what V2 stands for. V2 stands for the potential being set up by the first charge, right? As I am bringing the second charge to this location, I'm working against the field generated by the first charge. So therefore, this V2 is actually the work that needs to be done to counteract the field lines generated by the first charge. Okay? So Q2 V2 is the amount of energy being stored in this simple system. But of course, you can also look at the same system from a different perspective. You can also say, well, initially in space, I already have the charged particle 2. Then I bring the first particle from far away to this location, right? So in this case, charged particle 2 is already present, and I bring the first charge to here. Therefore, the energy is Q1 V1, right? Q1 being the charge of particle 1, and V1 is I'm trying to work against the field generated by particle 2. Okay? So together, Q1 times V1 is this amount. It's Q1 and this is V1. Okay? Now you compare the two. They are actually identical in quantity. It's just the nomenclature. The underscore, the numbering is different. But essentially they are the same, and they must be the same because you only have two particles, right? No matter which comes in first, essentially you only have two particles. It doesn't really matter which one is here first and which one you bring into this location. They're supposed to be identical. So this viewpoint, the two different viewpoints, whether charged particle 1 is present first or the second charge being there first, doesn't matter. But let's take a look at this mathematical equation. If I don't really care which particle is present first, I look at the entire system. Well, I have two charged particles separated by a certain distance. So this W2 stands for a generic expression for the calculation of the resulting stored electric energy. This W2 means I have two charged particles, and I want to write down the generic expression for the energy stored in two charged particles, right? So I'm looking at these two particles. They're already there, and I get to say, well, when I'm bringing the first charge into its location, I have to work against the electric field lines generated by the second charge, right? V1 is actually trying to work against the fields due to the second charge, okay? And I look at, well, I have two particles, so I also have another portion of energy. So Q2 is also having some kind of energy. So you sum them up. But do you notice something different? Something weird? The difference between this equation and these two results is a slight difference in your viewpoint. In the top, we somehow try to calculate the energy charge by charge, right? We only have two charges, but somehow in the top, we assume one charged particle is already there, so I only have to bring the second one into the place. But this equation is telling you I'm looking at the system as a complete system. So I don't really care which charge is coming first, right? So this is looking at the two charges as a whole. And therefore, I calculated the energy. I think each charge coming into this current location needs to accumulate work, needs to have some energy. But somehow when I add the two together, I noticed I overcounted, right? If you compare this result, this summation, to this, I double counted. So I have to divide it by 2. Is it clear? Essentially, the energy required to assemble this system having two charges with a separation of R1, 2, I only need to do this amount of work. And I know it because I assumed one charge is there already, and I only have to bring the second charge into place. But when I look at the system in a different way, I already have these two charged being there together. I just write down their energy equation. I add the two energy portions together. But when I am adding, I actually counted the energy twice. Right? This writing system is like saying, I have this, I have this, I add them up together. So I multiply by 2. Therefore, I need to divide it by 2 to get the real result. Okay? So why is this important? This factor of 2 is very critical. Otherwise, you mess up. Okay? So even for a simple system, only having two charges, you have to remember, if you write it down directly, energy plus energy, you double count it. So let's try to increase the complexity of the system. What happens if we have the third charge coming in? Alright, so now I have charge 1, charge 2, and charge 3. Again, I'm still looking at this problem in a charge by charge coming in sequence. So if I add the third charge into this location, I have to do additional work, right? And that additional work, delta W, the additional work that I need to do by bringing the third charge into this location is Q3 times V3. Now you have to think how to properly formulate V3. V3 is the potential being set up by both charge 1 and charge 2. So V3 actually has two contributions, right? This is the electric potential provided by charge 1, and this is the potential generated by charge 2. Right? When you bring this third charge in, it has to work against both fields. Okay? Therefore, the total amount of energy that you need to assemble this three-charge system is the energy you need for two charged particles plus this additional energy. Therefore, this is W3, the energy required to assemble 3 charges. Okay? So this is the correct formulation for the energy required. But again, we derived this correct result in a viewpoint that charge by charge is coming in, right? And therefore, we have the correct result. But what happens if you don't care about the sequence? You take a picture, so I have charge 1, 2, 3. I don't care about their coming sequence, but they're just there in space. So I blindly write down the energy required. This is what you get. I know that I have 3 charged particles, so I'm trying to sum up the total energy required. So I look at charged particle 1, right? It's there in space, but these 2 are also there in space because I don't care about the sequence now. They're already there. They're all there simultaneously at the same time. So if I have charged particle 1, then I have to work against the potentials of these 2 charges, right? Therefore, Q1, you have to work against V1. V1 has 2 contributions. The potential coming from charge 2 plus the potential coming from charge 3. And now I look at charge Q2. Q2. Well, it's there, and I have to work against the potentials of this 2. So again, Q2, V2, in this case, V2 also has 2 contributions, right? Q3, V3. So together, by a different viewpoint, I don't care about the sequence of charges coming in. I just calculate everything as they all are present. I have total of 6 terms, right? I have 1, 2, 3, 4, 5, 6. I have 6 terms. And if you compare this direct writing result to the correct energy being stored among the 3 charges, again you notice, ideally you only have 3 terms. But in this writing system, the direct, non-sequential, don't care about the timing of the charges coming, you have produced 6 terms. And each 2 of them are identical, right? Q1, Q2, Q1, Q2, identical. So again, you double counted. Just like the case for 2 charges. When you blindly write down these equations, you always double count. So you need to divide by 2. Okay? So I'm trying to explain this 1/2 factor in a pictorial way. Well, by the textbook, it just tells you you have to divide by 2. And the reason to divide by 2 is when you calculate this, blindly writing down, you count it twice. Okay? So again, the viewpoint is if you calculate charge by charge coming in a sequential way, you will have the correct description. If you view the entire system, all charges are there at the same time. When you write down the energy, you double count. So you have to divide by 2. Alright? But essentially, I mean, for practical questions, I don't think we have the privilege to calculate the charges coming in charge by charge. So usually we want to have a generic expression, right? We can have 1,000 or 1,000,000 charges. Therefore, you don't have the luxury of calculating the charge, one coming in by the next, right? So we want to have this generalized expression. So the electric energy is 1/2 summation of each charge multiplied by the corresponding potential. Suppose you have 10 charges and you're trying to calculate, well, the energy portion for the 5th charge, so K equals 5. So the 5th charge has to work against the other 9 potentials, right? So this potential Vk is actually another summation of all the potentials of all other charges. So J does not equal to K. So 1 to 4 and 6 to 10, right? So each charge in this case, assuming I have 10 charges, each charge being there has to work against 9 potentials. 9 potentials. Okay? So this is the generalized expression. And because we like to use the generalized expression, I have to explain and really focus on the fact 1/2 is essential. When you write down this equation, you're always double counting the energy. So you have to divide it by 2.